Welcome back. Jan LeCun, the director of AI research at Facebook, recently argued that deep learning has outlived its usefulness as a buzzword. As such, he proposed that now is the time for a new word to reflect some of the new developments in software. This word, as you may have guessed it, is differentiable programming, and today we're going to continue our mini-series by looking at its origins. So Johannes, differentiable programming is yet another buzzword in the world of technology. Do we really need another one?
I guess so. I mean, first, that's very interesting because you see, there is this AI. As soon as people start to basically have a solution that works for a problem, suddenly it's not AI anymore. It comes with a different name. So basically, AI is basically the generic term to say it's terra incognita. We don't know how to solve those class of problems, so that's AI problems. And then as soon as we have a solution, well, the solution has a name, and typically so far it has been a series of relatively iterative breakthrough with many iterations, and then it comes with a name that reflects, what is dominating as part of the numerical recipe in the solution.
Okay, and then we move on to differentiable programming. What's the story behind that? Where did the name kind of come from, and how did we get to that?
So the name comes from one of the ingredients that was powering deep learning, which is the idea of having a gradient-based optimization. So what does that mean, a gradient-based optimization? It means that imagine you have a model with potentially millions of parameters, and the way you're going to train those parameters is by having an objective function, a criterion. So that's basically something that tells you if your results are good or bad. And the idea is that whenever you look at a data point, you have the information that flow back through this function, and you can compute the gradient. The gradient tells you that if you steer the parameters just a little bit in this direction, it will locally improve the objective function just a little bit. That's the idea that is at the core of the stochastic gradient descent, which is the algorithm used to optimize all those modern machine learning algorithms, and all of deep learning, for example, works on that. So we have this gradient-based approach. Again, that's the idea, many parameters, and the idea is to move the parameters a little bit at every single time you observe a new data point, so that you can gradually get better. Simple idea, but then comes the problem is how do you compute this gradient? And by the way, gradient is just a big name for multi-dimensional derivative. So if you have, if in high school algebra you look at the derivatives, the slope of a curve, that's what you get in dimension 1. And if you have many dimensions, you're just going to refer at them as a gradient. And because you have many parameters, you want to compute the slope for every single one of those parameters. So bottom line is suddenly you want, because you have a gradient-based technique, you want to have a mechanism to compute those gradients. And it turned out that historically, neural networks, that's probably what came before deep learning, networks had all sorts of very complicated techniques, basically called backpropagation of the gradients. And it turned out that those techniques were, in terms of complexity to implement, in terms of performance, everything, it was complicated and kind of slow. Not desperately slow, but slower than what we have today. And one of the breakthrough that I would say that unlocked kind of differentiable programming was people started to realize about 10 years ago that they could use a technique called automatic differentiation, which is, by the way, 50 years old. I think it was uncovered first mid-60s, so it was quite a while ago, but it stayed completely, I would say, ignored from the scientific community at large. I mean, it was rediscovered multiple times, actually. But somehow those discoveries did not make it till, they were not people that were working on machine learning, so they were completely different fields. And so those breakthroughs remained, I would say, largely ignored. And so we had the machine learning community that was kind of stuck with the backpropagation techniques that were very complicated, very tedious to implement. And suddenly people started to realize that with those automatic differentiation techniques, you could compute the gradient for literally any program, not just any function, any program. And that was like something that was completely, I would say, game-changing in terms of implementation. Suddenly you could come up with a computational network that is like arbitrarily complicated, not just, let's stack more layers, but let's have like a complete arbitrary program, and then apply this very same gradient descent techniques. And that's where the term differentiable programming comes from, is from the idea that you're going to differentiate, as in compute the derivative of a program. That's where the name came from. And it reflects a bit the ambition of those latest advances in machine learning to think of, I would say, super ad hoc, super complex architecture for the computational network that can be like arbitrary programs, hence the name differentiable programming.
Okay, lot to take in there. So let's try and unpick a little bit of it. You said some of these ideas came around in sort of 50, 60 years ago.
Yes.
So it's not really like the rapid development that we're sort of seeing in the media and things like that. So it was actually quite an iterative approach to kind of get to differentiable programming.
Absolutely, but the reality is that even deep learning before that was super iterative, and neural networks before that were super iterative. I mean, the pace of progress have been actually quite rapid for the last 50, 60 years. It has been incredibly rapid. And what is intriguing is that in the early, let's say, 60s, people thought that, if we can crack multiplication, exponentiation, or all those hard calculation, then identifying a dog will be like super easy. After all, any idiot in the street can say this is a dog, but it takes like super trained mathematician to compute a logarithm. So obviously computing a logarithm is way more complicated than identifying whether you have a dog in front of you. And the biggest surprise came from the fact that it's actually the reverse. Those like problems that we completely take for granted, such as, for example, being able to keep your balance while standing on 2 feet, it's tricky. I mean, it's actually, if you just stop moving, you just fall. So it's completely dynamic. It's not, standing upright, having like a bipedal robot is like a nightmare, engineering nightmare. It's much easier to have things that just works on wheel and that are completely stable by design. So the sort of like super simple problems like standing upright, identifying if what you have is in front of you is a dog or a chicken or something else completely, like just a poster with a picture of a dog in the poster instead of having a real dog. Those problems are like very, very difficult. And the problems like computing logarithms are actually super easy with the computing architecture that we have. So it was like a big, big surprise, and it took literally multiple decades to realize how much we had to discover to even start tackling those super fundamental problems. Hence, the fact that we have been talking about AI for like, a series of decades, that the progress have been very real, very steady, but it's just that there was so much to discover that it felt maybe from, I would say, an external viewpoint that it was kind of sluggish just because people set the wrong expectations at the very beginning. But it's coming, and it's literally making still a lot of progress, and we now realize that we have probably a long road ahead of us still.
Okay, and you mentioned sort of neural networks. Kind of the inspiration behind those neural networks was very much the brain and how the brain kind of functioned. So how about differentiable programming? What was kind of the inspiration behind that?
I mean, the key, very interesting insight was the transition from neural networks to deep learning was the idea to completely pretty much give up on all the biological inspiration and to realize that if we wanted to move forward, we had first to kind of discard pretty much entirely the inspiration, the biological inspiration, to focus on what is actually working with the computer hardware that we have. So that was one of the key insights that drove deep learning. And so that the next stage about from deep learning to differentiable programming was one of the key strengths of deep learning is that you can build machine learning models in a way that is extremely modular. You can compose them, you can stack them, you can concatenate them, you can mix them in plenty of ways. And then when you move forward with this idea, which is, by the way, is of prime interest for supply chains. Why? Because we want to mix things such as prices, products, clients, locations, containers, all sorts of very diverse objects that you need to put together to resolve those quantitative supply chain problems. So you need to address all this diversity. And then you realize that, well, if you start having machine learning models that you can compose in many ways, what do you end up with? When you start really of thinking, what should I do to really make this whole thing like super flexible, not just like a little bit flexible, but like really flexible, really versatile? Well, you end up with a programming language, very literally. And the interesting thing is that people started to actually in deep learning, they started to build toolkits that were closer and closer to actually programming language. And even, for example, Microsoft, they released to the public a couple of years ago part of CNTK, their computational network toolkit. So that's their deep learning toolkit. They had BrainScript, which was actually a domain-specific programming language for deep learning. But the next stage consequence was, let's go, full programming. And the good news is that with this automatic differentiation techniques, we suddenly had a way to make it, I would say, relatively straightforward and easy as far as technology was concerned, to actually design and engineer the toolkit itself.
Okay, so it's kind of like a Lego brick kind of approach, and you're combining different blocks from different places and combining those kind of models in different ways. So how does that actually work in practice? How are you actually implementing this coding behind it?
So Legos, I think, was pretty much the archetype of what people had with deep learning. Indeed, it was about combining blocks, but in ways that were fairly, I would say, fairly limited. I think it's a spectrum between deep learning and differentiable programming. There is no clear delimitation. But clearly the difference was that people transitioned from Legos that were where it was just a matter of assembling those parts, to programming where you can go to do the same thing but with like programmatic expressiveness. So it's a whole new level. So for supply chain, that means that you can revisit problems and express your solution, what you try to do, in a way that is much more succinct, in a way that is much more to the point of the problem that you're trying to solve. So what am I talking of? I'm talking of, for example, let's try to jointly optimize, pricing, demand forecasting, and stock allocation. And when you think about it, all those things are completely coupled. I'm forecasting the demand, but I know that if I tweak my pricing strategy, I will modify the demand. If I modify the demand, well, it has an impact on how much I should produce and stock, because obviously, the demand will be different. So we have all those things that are actually completely coupled, and they have dependencies that you can literally write down. I mean, the dependencies are not, that complicated in a way. It's, if I have more demand, I need more stock to fulfill the demand. So far, it's pretty obvious. And if I price, I put the price at a higher point, then for the demand that I will preserve, I will have a higher margin. So there is plenty of things that are like complete down-to-earth calculation. But the question is that how do you put all those ingredients together in order to do something that is both a prediction and optimization? And the answer is differentiable programming with specific techniques where you can write those programs that will leave a lot of blank space. That's going to be all the parameters that you want to optimize. And you will have a supply chain scientist writing that and the proper technology to do the optimization.
So what you're saying with these blank spaces is you're actually writing a program where you don't actually know all of the answers.
Yes.
So how does it actually know, how can you know that and have confidence that you're actually going to get to the right answer if there's these blank spaces there?
So indeed, I mean, the problem is similar. Fundamentally, differentiable programming is in the realm of machine learning. You know, you're learning. So you don't have any guarantees that you will get good results. That being said, I don't think that nowadays, you know, that's the very same applies for, let's say, deep learning and all the previous machine learning techniques. And I think nowadays, Go and chess, I mean, those machine learning programs have now outcompete all human players. So it's not as if, you know, we didn't have clear sign that it's actually working even, you know, beyond human capacity for problems that are still fairly narrow, as opposed to identify where the dog is in a messy urban, I would say, environment, which is a much more difficult problem.
Okay, you mentioned sort of some of the supply chain perspectives for differentiable programming. From a research and development kind of perspective, how close is the stuff that we're doing here at Lokad compared to the stuff that the Facebooks of this world are doing into differentiable programming?
I believe, you know, the super large tech players, you know, Google, Facebook, Microsoft. I'm a bit envious of, you know, the budget that they have for research and development. I mean, at Lokad we are doing our best, but let's be realistic. I don't have even, you know, 1% of the AI budget of Microsoft or Facebook. That's the reality of, I would say, most B2B companies. Right now, those markets are still fairly niche, and there is no company in supply chain that would say we have, 2,000 AI researchers. I don't think that there is anybody who can claim anything close to those numbers. But nonetheless, the good news is that those giants like the Google, Amazon, Facebook of this world are actually publishing a lot. So most of their research, you know, is published. And thus it means that one of the key challenges that we face at Lokad is to keep a close look at all those publications and steadily, you know, take inspiration from that, re-engineer what they are doing, but from a supply chain mindset. Because again, keep in mind that those very large teams, they are working on the big AI problems, which are computer vision, speech recognition, speech synthesis, natural language processing, which is not at all what people are trying to solve as far as supply chain are concerned.
So how could you go from those big AI problems like image recognition, speech recognition, how can they be related at all to supply chain?
Because actually, people have been uncovering, I think that's the key insight of the progress for the last, you know, couple of decades, is that to think of the core mechanism of learning, the core mechanism behind an efficient, I would say, scalable numerical optimization. So what is very interesting is that most of the insights that they are uncovering are not specific to images. They are more at the fundamental level of what does that mean to even learn anything from data. That's the crux of that. I mean, obviously, some publications are very specific. You know, it's just a nice trick that only works for images. But there is many publications where the trick, or, you know, the insight that is uncovered is actually not specific at all. It just happened that in order to validate, you know, the insights and experiments, and they have to engineer a solution, and this solution is engineered for images. But the trick could be, you know, declined on completely different problems. It will not necessarily work with the same efficiency on completely different problems. But the good news is that sometimes it will even work better. So you see, you have something that is like a trick that was discovered that was nice for images, but not necessarily a game changer. but so published nonetheless as worthy of novel and making the science progress further a little bit. And then you realize that when you apply this technique to a temporal graph from a supply chain context, it suddenly what you can achieve leaps forward. So it goes both ways.
So what's the main benefit then from a Lokad perspective of differentiable programming? Is it this kind of idea that you can answer all those unknowns that are there in a supply chain and all those blank spaces where you don't know actually what's going to happen in the future?
The big challenge that we face in supply chain is how can you have like predictive modeling, and predictive optimization that do not betray the business. You see, it's non-trivial because it's not about getting answers in general. It's having a very specific class of answers, of decisions that optimize the business, not in a generic way, but in a highly specific ways, which are exactly the business drivers that you're defining. Because again, we do not try to have these AI techniques, whatever, to uncover what are the business goals. No, the business goals are actually established with, it requires like human level intelligence to define what you're trying to do, what is your strategy, what is your perspective, and etc., etc. So the problem has a lot of structure. And the biggest challenge is that how do you make sure that the numerical recipes that you're crafting is actually aligned with those business drivers. It's very difficult. Usually you end up with the problem that you have a hole that is round and your tool is square and it just do not fit. And the differentiable programming is a way to be much more expressive. And this is the key to make sure that you can, frame a numerical recipe that is actually fitting the business problems that you have in front of your eyes. If you have access to a programming language, then you're so much more, I would say, expressive and versatile. Suddenly it becomes, in practice, a lot easier to make things fit.
Okay, and to start sort of wrapping things up, you mentioned at the start that differential programming was very much the start of a long road with plenty of challenges ahead of it.
Yes.
So where are we on that road, and what are the biggest challenges that we're going to face?
The biggest challenge is probably to establish identify a series of constructs and building blocks, programming building blocks that really works well for supply chain. So remember, automatic differentiation lets you differentiate any program. True. But as you were pointing out, it's not because you start pouring parameters in your program and you say, well, anything will work because I can optimize my parameters. No. The reality is that it's not any kind of program that will work. Yes, you can differentiate any program that has those parameters, but the reality is that if you were writing a program at random with parameters in the middle, when you trigger your optimization, your automatic differentiation, the results that you will get will be complete crap. So no, we need to identify specific ways of crafting those problems that actually yield results that are not only good, but also very steady and reliable. You see, we want to have things that we can move to production. So being better on average, it's not sufficient. You want to have something that is not only better, but also very reliable. And so you don't generate, 1 times out of 100 something that is like critically bad. You want results that are like very steady, very reliable, that do not, I would say, fail in catastrophic ways once in a year. Okay. And that's still probably partly ahead of us.
Brilliant. All right, we'll have to leave it there for today, but thanks for your time.
Thank you.
So thanks very much for tuning in. We'll be back again next week with our last in the mini-series on differentiable programming. But until then, thanks for watching.